Okay, so last time we discussed that, and this is the same for any strength design that you do. You're gonna have here a capacity versus demand. And in all cases, you'd like to see capacity higher than the demand, or at least it's gonna be equal to it. V sub U, we refer to it, this is gonna be the demand, and the capacity is gonna be phi Vn, very similar to phi man, in terms of the way it looks like, the formulation. So phi is gonna be strength reduction factor, and the V sub N is gonna be nominal capacity and shear. The other one, phi man, is gonna be nominal capacity moment, and then again you multiply by another phi, different phi, and with that you get the final capacity. This phi factor is 0.75 for shear design. It's gonna be constant value. There is no chart to find it out, it's just a table, and it says for shear it's gonna be 0.75. Demand, we're gonna be following the same load combinations that we have used before, which is typically for this course is gonna be 1.4 dead, right? Versus 1.2 dead plus 1.2, 1.6 live. So it's gonna be these two components that you're gonna be seeing. And of course, you're gonna be trying here both options for both load combinations. And at the end, you're gonna be picking the one that yields higher forces. And this is gonna be kind of like the critical case that you need to design for. So this when it comes here to V sub U. Now phi Vn, again, is gonna be composed of concrete contribution to the strength and steel. So V sub C is gonna be the concrete strength. V sub S is gonna be the steel strength. Again, phi factor is constant, 0.75. The concrete strength is just constant. It just based on the strength of the concrete, and it's gonna be based on the section width and depth, like cross-section area. It says here 2, which is a shear factor. We call this shear factor. So let me write it down here and say this one here we call shear factor. The shear factor here is just 2. It's like the constant. Square root of F prime C, this F prime C, the concrete strength, it has to be in psi, as we said. BW is going to be section width and depth. So, okay, yeah, makes sense. And this gave you the concrete strength without the phi factor. If you like to see the final concrete strength, you just take this V sub C, multiply by the phi factor here of 0.75. Same thing for the steel. Now for the steel, it says here Vs equals to A sub V. We said A sub V like the quick example I gave in the lecture. When you have a tie, and let's say the tie is going to be number 4, and then you have 2 legs. For each tie, A sub V is going to be total cross-section area of all legs for one tie, for one stirrup. Going to go back here so that we also talk about the S, the spacing, and A sub V. We looked at this picture, then we say, well, how many bars are you talking throughout? You're cutting here through 1 and then 2 bars for the same stirrup. Excuse me. So you're cutting here through 2 rebars of the same stirrup. So I'm going to say here A sub V is going to be equal to A 2 times A sub S for each one of these 2 bars. S is going to be the spacing between 2 ties or 2 stirrups. And this is going to be longitudinal direction of the beam, meaning one support is going to be, let's say, in this side, and one support is going to be in this side. Here's the width of the beam, and here's the depth. So this is going to be B. Distance from here to there is called here the depth, D. So I can write it down here. Just put it there. Here's the depth. No, not this D, the lowercase. So now I understand A sub V. Let's say if I have here 3 vertical rebars for the stirrup, as in one set. Now my A sub V is going to be equal to 3 times AS for each one of these times. While S is going to be the spacing. So, okay. Let me see here. Let me look at the equation. Equation says the steel strength in shear for the ties is going to be equal to A sub V, total cross-section area of all ties that you're cutting through, times FYT. T stands for ties. So this FY, if you have grade 60, so I'm going to say here, Fy equal 60 KSI for steel what? Grade 60. Times the depth, divided by S, which is the spacing we we're just talking about. This one here, you cannot just put tons of reinforcing for ties to give you the strength. You have a maximum. And this maximum, again, is given by this equation. This maximum is not over this stress. You don't want over the stress here. The beam, in terms of the concrete, when you're adding tons of steel and the concrete beam section itself is not that strong. So we have this limit. And if you look here at the shear factor, again, is going to be equal to 8, and it's going to be for the maximum shear strength provided by steel. So when you look at this 8, the square root of A prime C, B times D, compare it to the previous one, the concrete strength, it shows here 2. So the shear factor here is 2, and the shear factor here is 8. Which means code here is going to be limiting the steel strength for ties to be roughly about 4 times the shear strength by concrete. So let's say concrete is going to give you here, if I may just put a quick example, concrete is giving you here 10 kips. What is the maximum VS that you can use here in this equation? I'm going to say the maximum is going to be 40 kips. Why? Because it's going to be 4 times than the concrete strength. Concrete strength is going to be controlled by this constant, 2 square root of A prime C B D B W D. Look at the maximum steel strength. You can't go beyond than this. You can add tons of steel, but cannot help you to go beyond 40 kips. So this 40 kips is going to be the maximum. Even if you put more reinforcing, it's not going to help out because you're limited here to 4 times the strength of the concrete. Any questions? No questions? We're good? All right. Now, let's say here, because we have this equation, the equation says V sub U and PVN. So let me throw here some numbers that we discussed last time, but I'd like to confirm it again. Let's say here that I have V sub U equals 50 kips. Let's give me the demand. Concrete can resist, which means I'm going to say here phi VC, right, equals, I'm going to say here 70 kips. So once you look at this equation here and the values, right, you say here, let me go back one step to this slide. Look at this equation here. V sub U is 50 kips. PVC is 70 kips. Look at this equation here again. This means that I have enough strength in the concrete than the demand. When I look at this equation here, I'm going to say this value here, which is how much? 70. Coming from only the concrete. This means I don't need any steel. Why? Because I have enough strength in the concrete than the demand. Your demand is only 50 kips. Concrete here gives you 70. So concrete gives you higher than what you need. Now the question is, do you really need to add any ties to your beam, or can you just put the beam without any stirrups or ties? To answer this, I'm going to be going here with you through this condition given by the code. It says here, is this V sub U, the demand, is going to be less than or equal 1/2 of the concrete strength? You don't need any ties. So let me check this condition. V sub U is 50. It is not less than 1/2 of this, the 70, because half of the 70 is 35. So actually this condition doesn't happen. So in a case like this, I need to add ties anyways, or stirrups. And to add ties, you need to go here to AV minimum, and it's going to be given by 2 equations. And of course, you're going to be using the one that yields higher reinforcement area. Any questions before we do an example? Yes? Here's one tie. I can have a couple of this tie A. If you like to call this tie A, it has two legs. I can put them in one set. So the spacing between this tie and this tie is going to be 0. They are touching each other. So in this case, I can say AV is going to be equal to 1, 2, 3, 4 times AS for one rebar. So this is good. I mean, if you really need more legs, you can keep the spacing the same and you can just add more ties. Like here is one tie, which is A. You just add another one, it's going to be touching it. And also you can tie them to each other, you know, some wires. You can do that. One example. This is the same example that we have done when it comes to FEMN, if you guys recall that. It says here, determine the shear strength adequacy for the beam shown below, the beam section shown below. The beam center to center line span is 22 feet, while the beam clear span is 20. So, okay, there's something called here center to center span, something called here clear span. So what do you mean by clear? What do you mean by center to center? I'm gonna say, if you guys recall, this is gonna be the beam that we do the analysis for, right? It says here the clear center to center span, which means center of support to center of support is 22 feet. Let's give it the total span. Center to support to center of support. But the clear span is 20 feet. Look at the column here. Here's a beam, two columns. So here's the center line, and the distance here is 22. Here's a column, here at this line here. From face of column to face of column, if I may do another line here, to this face of column is 20 feet. This is what we call here clear span. So what's the clear span again definition? Is going to be from face of support to face of support. You can call it support, you can call it a column. It's the same thing, right? It's a column supporting the beam. So the spacing here, again, L clear is going to be 20 feet. The load is 2.92 kip per foot. So I'm going to go back a couple of slides just to continue the problem. It says dead load is going to be 1.5, live load is going to be 0.7, strength of concrete is going to be 4,000, F sub Y is 6,000. I guess we have the width as 10 inches, and the depth, if you recall for this problem, that was 13.5 inches. This previous example that we have done before. I guess okay, dead load on live load, we try the two load combinations. One of them, the 1.4 dead, is going to give you here 2.1 kip per foot. The 1.2 dead plus 1.6 live is going to be 2.92. Now, which one is higher? I'm going to say this one is higher. I'm going to be using this value because it controls my design. Now, let's move forward. Here's again the beam. 2.92 kip per foot is the demand load. If you like here to look at the reaction is going to be 2.92 times 22 divided by 2. So the reaction is going to be 32 to the left and 32 to the right. Now, where is the shear demand? This is going to be my question. Shear demand, I'm going to go back here a few slides. Just to remind you with the one slide that we discussed about the critical section for shear. You can say shear demand in a beam like this is going to be at D distance away from face of support. So where's face of support? We can say this is going to be face of support. You go D distance as if you are going to be going here as 1 to 1. 45 degrees. Here's depth. Here's also the depth. From here to there is also D of the beam itself. I'm going to put it here D. Now let me do the same thing here in my example. It's okay. So this is going to be face of support. We're going to be going here 1 to 1 because the distance from here to there is equal to D. You see this distance here from this point to this point. If you go here 1 to 1, it's going to be 13.5 inches. Actually, this is going to be my critical section for shear. It's going to be right here. This one here. So my goal is to find out the shear because it's going to be actually V sub U. This is here my V sub U, which is this value from here to there. This value here. So how do you figure this out? I know if you like to draw the shear diagram, you start with the reaction, you end up with the reaction, you do a straight line, sloping line. So my task here is to find out the shear at this section, at this location. So the question is, how much is the distance from here, from the center of the support, to the critical section? I'm going to say first, it says here that this is 20 feet. See this here, 20 feet? Face of support to face of support. And this here, 22. This means that I have 1 foot to the left, and 1 foot to the right, which is 1/2 of the column width. The column width here is how much? 2 feet. How is that? Because you have here a foot to the right and a foot to the left. And say, okay, so I have here, this is going to be 1 foot. And this distance here is going to be 13.5. So add this 13.5 divided by 12 plus 1 foot. Okay, here we go. Look at this. 13.5 divided by 12, right? This give you 13.5. If you like to add also this 1 foot, you can add it. So someone here can say V sub U equals the reaction. How much is the reaction? It's going to be 32.12. Subtracting this distance from here to there, from the center of the support to the critical section for shear. How much is that? I'm going to say 1 plus 13.5 divided by 12 times the slope of this line. And the slope of this line is 2.92. Can someone help you with the math of this problem? Yes?
I got 25.915.
915. Yes. Right, I guess this is very close from this number, right? Am I correct? Yeah, it is. It's 25.9, 25.915, right? 92. There is more than one way of doing the analysis to find out the critical section for shear. So one way is to find out the reaction and then reduce it from this point to that point with the slope of this line, knowing that I have the distance from here to there. This distance is going to be this value here in this box in feet, which is this distance here. How is that? I'm going to say it's going to be a foot plus 13.5 divided by 12, distance from the center of the support to the critical section for shear. 1 foot plus 13.5 divided by 12. The slope of this line is actually equals to the load that you apply to it. So I'm going to say here, slope of this line is equal to W ultimate, right? Which is 2.92 kip per foot. All right. I know slope of this line, right? So you take the 32.12, you do the slope down, you end up with 25.9 kips. This makes sense. So now I have the demand. Why do I need the demand? Because if you read the problem back again, it says here determine the shear strength adequacy, which means find out the strength, find out the demand. Now to find out the strength, you have concrete contribution and steel contribution. Concrete, I know the width is going to be 10 inch. Depth is going to be 13.5. Concrete strength is going to be 4,000. For the steel, I have number 4 ties at 14 inch. So what is a 14 inch here? I'm going to say this 14 inch means the spacing. This could be S. S equals 14 inch. Anything else? I'm going to say yes. What is A sub B for each one of this number 4? I'm going to say A sub B equals 0.2 square inches. Right? For just one bar. A sub B for one bar. How about A sub V? I'm going to say A sub V is going to be 2 bars because it's going to be 2 vertical bars. 2 times 0.2 is going to be equal to 0.4 square inches. So I guess now I have all the information from this slide and I should be able to move forward. But let me add to it. I'm going to say F prime C equals 4,000 psi and Fy for the steel 60 ksi. I said, okay, this is all the information I need from here. So I'm going to be taking this, going to be moving forward to find out the strength. Here's the information I have from the other slide. First, phi VC. Phi factor is a 0.75, the constant. We say it's going to be constant, right? Same VVS. Look at this. Same phi. See the phi factor, 0.75. We can't change it. It's the same. For the concrete, is going to be 2 times the width, and my width is equal to 10 inches. Depth, 13.5. So I'm going to say this is going to be cross-section area of the concrete section. 10 inch wide, 13.5 deep. 2 is the constant, the shear factor. Square root of F prime C, yeah, the 4,000. And then at the end, this is going to be in pounds because this is going to be here in what? I'm going to say 4,000 psi. You divide by 1,000 to put it in kips. Now we have 12.8. I'd like to keep this in mind. Your demand is how much? 25.9. I said, okay, 25.9. Let me keep on memorizing this. I really need this, right? Just understand where I'm going to be at. Say, okay, this is a demand, 25.9. So the concrete by itself is not enough to resist the demand. So contribution of the steel here is going to be needed. I say, okay. VS, based on the provided ties, is going to be equal to AV. If you remember, AV equals 0.4 square inches. Here we go, 0.4 square inches. Times 60 what? KSI for F sub Y, right? Times the depth, 13.5. Depth, 13.5. What by the spacing? You guys remember the spacing? From the problem, it was 14 inches. So I put here 14. How much strength do we gain out of the steel? Just out of the steel. It's going to be 23.14. But this is not the total strength. The final strength, I need to take this value here multiplied by the 0.75. See what happened? I've taken here the steel strength, multiplied by 0.75. Now I have 17. Concrete gives you a strength of 12.8. Steel gives you a strength of 17.36. Is this okay, ratio-wise? What is my limit? If you remember, my limit was 4 times than this value, right? My limit for the steel, I'm going to give back here a few slides. Limit for the steel is going to be 4 times than the concrete. Concrete is going to be shear factor of 2. The steel gives you here a maximum of 8. So now let me move forward to the problem. And now let me compare 12.8 versus 17.36. This is like 1 and a fraction. It is not like 3 times or 4 times. So I should be fine. Total strength by concrete and steel. You just add these two values to each other. Look at this. Take the 17, let's give you the steel contribution. Take the 12.8 concrete contribution, and then here we go. You have a demand, a capacity of 30.16, greater than the 25. Your section is good. You have no problem. This beam is strong enough. It has enough strength to resist shear. Say, all right. How about the minimum reinforcement? I mean, is this beam here with the amount of ties, number 4 at 14, is good code-wise? Did we provide enough reinforcement for shear reinforcement here? I'm going to say, I don't know. I need to check this out. So here's the 2 equations for the minimum. Okay. Here's the equation 0.75. This is not phi factor, it's just a constant in the equation. Square root of f prime c, the 4,000, width is 10 inches, and the spacing is 14 inch, divided by fyt, which is 60,000. Here's the minimum. A sub v is 0.11. If you use the other equation, 50 times also constant, bw is 10, s is going to be 14 inch, fy 60,000 pound per square inch. Yeah, 0.12. Which one that I need to satisfy is going to be the highest of the two. It's going to be the 0.12. How much do I provide? This is going to be the question now. When it says here a minimum, you need to compare it here with the AV provided. I'm going to say we have provided two legs. Each one of them, it has 0.2 square inches, which means 0.4 square inches. This is more than the 0.12. So we're good. We have more reinforcement than the minimum needed by code. So let's say this case here, this is going to be AV provided. This is what we have in the problem. We were able here to cover the strength. When you look here at this, yeah, strength is covered. 30 kips versus 26 kips. Now look at the minimum reinforcement, we're good. Any questions? Right, one slide is left here. This is going to be the curve, the shear. Here's the shear diagram. This is going to be the reaction. You remember the reaction? If I may take you back here. Yeah, here we go. This is going to be the reaction. This is going to be the critical section for shear. This is going to be your demand, right? So this part of the shear diagram is just taken by the column and the 45 degrees. Because the column actually, it goes up to here. Look at this. If you remember here, the column width is 2 feet. So 1 foot to the right, 1 foot to the left. So here's 1 foot. The reaction 32.12. The shear at face of support is 29.2 from the shear diagram. Up to here, this left side of the diagram is just resisted by the column itself. The beam is not supporting this. It's giving the column, look. It's giving here within the column. Even this section, I'm gonna take it all the way to here. Even this section, all of this is just supported by the column side. And this is gonna be supported by the beam. That's why we have this critical section for shear is gonna be right here. Meaning, all of this shear from here to there is taken by the column and the hunch, and by this 45 degrees. It's okay. So where's the shear that I need to resist? I'm gonna say this give you the shear that you need to resist. Here there is give you this section of it, right? This triangular shape. Okay. Just we're gonna put it here aside. The concrete itself. Do you know how much concrete resists? Let me go back here. Concrete by itself resists 12.8, right? And the steel, 17.36. Let me try to memorize these two numbers. 12.8 concrete, 17.36 for the steel. When you look here at this diagram, look at this, PVC. This concrete here is resisting this strength values, right? All of that is just taken by the concrete. And this blue triangle shape is resisted by the steel, the stirrups. Conclusion is this amount of steel that we provided is good, and the concrete and steel, both of them, they are able to support the shear demand applied on this beam. With that, I'm done with this slide. I'm done with today's lecture, and I'm going to be working with you now on the project. So please go ahead and ask questions if you have any.
Professor, I'm a little confused on how come there, if you go up to slide number 16,
Yeah,
which are you?
It is a reaction at support. U stands for what? Ultimate. This RU stands for ultimate. And the right and the left side, they're all the same, right? But this one here is R sub U at where? Let me point here for you. It's going to be actually this one, right? Because Some people would think about it this way. You say you have center to center span, you have also clear span, correct?
Yes.
You have two spans. So one person here is going to be looking at this and say, this is going to be the reaction at center of support. And this is going to be the reaction at face of support. Since we have two spans, right? We have clear, we have L, center to center. So if you take this 10 feet, 1/2 of the 20, right? Multiply by 292, you're going to be getting here 29.2. This is not the reaction at the support. This is going to be the reaction at face of support. If you like, you may change the name of this. You can call it, for example, V at face of column. You can call it this way, right? It is
Yes.
not the
Okay.
shear that you design for, because you're going to be designed for lower shear, right? At face at 45 degrees from face of support. And in reality, you don't really design for the actual reaction at center line. You don't design for this reaction with this amount of shear at face of support. You design for a shear, which is going to be at the critical section for shear, according to the code, is going to be at D distance away from the face of support. Did I answer your question or?
Yes. Thank you. That makes sense.
No problem. Thank you. More questions?
Can you go over how you got D again?
D,
The
the depth?
no, the spacing. Oh, is that what it is? The spacing from the
The
face?
spacing S, spacing was given the problem.
I'm talking about like if you go back to the example problem where you were at right now, the R of U. You
Yeah,
see how the under the second line there says D is equal to 13.5. That's the effective depth.
yeah. And
Okay.
actually this is taken, should I bring the old slide set with it? Or
No.
you remember
I
this
got it.
slide set?
Yeah.
That was kind of our favorite section that we use. We try to change it every time, right?
Yeah.
And here we go. This is the one, right? 13.5.
Mm-hmm.
This is exactly the same example that I repeated. I just
Mhm.
took the same values for the shear and just calculate out.
Okay.
Yeah, and if you like, if you remember the slide set,
Yeah.
actually this gave you slide set number 4, right? And if you like to see the calculations for it, this gave you slide 15 at slide set number 4.
Mhm.
Right, very good. More questions?
Professor, could you go over VU again?
Sure. How we came up with this V sub U, right?
Yes. Yes.
So I'm gonna say here, you have some load applied on the beam, right? And for this load on the beam, you have center to center span, 22 feet. What we'd like to do is to find out the critical section for shear, which is gonna be here. And if this is gonna be the shear diagram, this actually is gonna be the shear demand on the beam, right? This is gonna be V sub U, this value here. How's that? I'm gonna say, well, you go here to the face of support, which is 1 foot away from the center line, and then you go D distance. And we know D distance is 13.5, right? Are you with me about the 13.5?
Yes.
Okay, good. So the distance from the center of the column to the critical section for shear is going to be equal to 1 foot plus 13.5 inches. We put it all in feet because the span also is given in feet and the load is given also in feet. So it is just easier if I put also this distance to be in feet. It's going to be equal to 1 foot plus 13.5 divided by 12. So, okay, 1 plus 13.5 divided by 12. So what is that distance? If you like, you can call this distance here. I can call it, let's say, X from here to there, right? Let's say this distance is called X. Where do you use this section again? You're gonna say, oh, yeah, this distance is gonna be this distance here that they have in the box, right? How to find out the shear here? You take the reaction, and then you decrease it by how much? I'm gonna say by x times the slope of this line. The slope of this line, according to what we learned in statics, is gonna be equal to the load, right? So the first derivative of the shear diagram is gonna be the load. Very good. Did I answer your question?
Yes, thank you.
Right, no problem.
Yes, definitely. Thank you.
No problem. Should I switch to the project?
Yes, please.
All right. So the project is actually on the slab design. We have here a good example that I'd like to look at. I guess you guys are good with submittal 1. Am I correct?
Yeah.
All right. Let's look here at submittal 2. I'd like to design here a typical one-way concrete slab at the typical floor. And also another one is gonna be at the roof level. Okay. And they give me options so that I don't struggle with the assumptions. So, all right. Let's give me one strip that I'd like to work with. Give me that simple. Now, for you guys, this give you a support because the beam support the slab, right? Here's one support, another one. A third support, right? It's gonna be like a continuous beam with lots of supports. Now, how big is this span? I need your help. How big is the span? This L, do you know? Someone help me with that? The spans from here to there, and how much is that? The span equals? Yes, 1.
For that section right there,
The spans give you distance from here to there, which is how much is there?
9.33.
Okay, how did you do it?
If you look on the left, the L of Y,
Yeah,
it's 28 for 3 of them.
yeah, divide by
So,
3.
yeah.
All right, very good. And then I have this continuous slab section, right? On all of the supports. Now, do I have the weight on the slab? I'm gonna say yes, I have it. From where? I'm gonna say submitted 1. CFW ultimate. Okay. How about the moment diagram? If I have this W, I'm gonna say moment diagram, I'll be using this. We talked about this, right? So your moment diagram, maximum positive is gonna be 0.08 WL squared. So the span is gonna be 28 feet divided by 3. W, you have it from submittal 1. Then you have 0.08 WL squared. It's gonna be maximum positive. How about maximum negative? So okay, it's gonna be this one. You have also the weight. You have the span is gonna be 28 divided by 3 times 0.1. It's gonna be 10% of that. So maximum negative and positive, I can get it from here. I'm gonna say, how about this? I'm gonna say this is gonna be 0.025 less than 0.08, so I don't need it. How about this? Again, 10% of W squared. It's gonna get repeated. So I have here the maximum negative, maximum positive. With that, I'm done with the moment. So what should I do after this? I'm gonna say, well, now you have moment, and then you have one slab on the typical floor, and one slab is gonna be at the roof level. You have 2 different load criteria. And then you look at this example. You just do it according to this example. Where'd you get the depth from or the thickness? I said, well, let's look here at the problem. It says here slab thickness, 8 inches. Total thickness, right? Like in our example here, it says slab thickness is how much? Let me check. Do we have the slab thickness? Yeah, it's 10 inch. Out of the 10 inch, how much was the depth? Do you have here the depth? Is it written here anywhere? Can someone help me? You see here the depth? Let me check. Depth, I have taken here the slab thickness, subtracting 1 1/4 of an inch. You can do exactly the same. Take the 8 inch, you subtract 1 1/4. It's gonna be good assumption for the clear cover in the concrete slab. So, okay. So what else do you need to finish this problem? It says here check if number 5 at 16. And then the question is, how do you find out AS for number 5 at 16? You find AS for 1 rebar times 12 up by 16, which is the spacing. This will be the amount of reinforcement that you have for each 12-foot strip. How about in our case here? It says here, check number 5 and number 4. Prefer the spacing is going to be 12, 14, and 16. So you try. Pick something and prove that it's going to be good enough. Does it make sense? How about the spacing? I'm going to say, yeah, try number 5, 0.31 square inches for 1 rebar. Try number 5 at 16. Because when you increase the spacing, you're going to be getting less steel, which is going to be your target. You'd like to save in materials. You don't want to go 12 inches if number 5 at 16 is good enough. So you try number 5 at 16 and you see if it's going to be good enough or not. This is what you need to do, which is very similar to what exactly we have here. Here's number 5 at 16, right? You consider 12-inch slab strip width, and then you find out Feynman. If your Feynman at the end of the day is more than the demand, where'd you get the demand from? Again, from this moment, then you're good. If not, you add more reinforcing. How do we add more reinforcing? We can use the same rebar size, number 5, but we make it at 14-inch. We reduce the spacing. When you reduce the spacing, it means that you are adding here more steel. Very good. Any questions on the project?
For the reinforcement, are we just is it for tension only? Or
Yeah.
are we also okay?
No, just for tension.
Right.
No compression. It's gonna be very simple.
Right.
Who needs more time for this project to submit?
Yeah, I probably do have
Yes,
to do.
definitely.
Okay. I'll open it to end of what? End of tonight? This evening? I'm listening.
Sunday.
Yeah,
Who
need
said
some
it?
more time.
Who said that?
Sunday.
I would like till Sunday. Pretty busy during the week.
Yeah, I got midterms this week.
You got midterms.
Yeah.
What day is Sunday?
March 5th. Wait. Yeah.
Right, extended. Good luck.
Professor, is the roof level any different since it's the same thickness?
Is the life load?
Is the roof level submittal any different since?
Yeah, it is the life load.
Oh, thank you.
You can end up with the same reinforcing, right? But the life load is going to be different. Your demand is different.
Okay.
And also be sure that you check the minimum reinforcement, right? Don't you have minimum reinforcement ratio? So sometimes you don't need lots of steel, but you need to be sure that you check this. Someone's going to say, where's this minimum reinforcement ratio? I'm going to say, it's right here in the same slide set. You see this, you need to back check this at the end of your design.